What if everything we thought we knew about the beginning of the universe was just one chapter in a much larger story? Picture this: long before the fiery birth of our cosmos in the Big Bang, another universe might have existed, its faint whispers still echoing through the vast expanse of space. These aren't just wild ideas from science fiction. Right now, scientists are hunting for clues hidden in the oldest light we can observe, the cosmic microwave background, a ghostly afterglow from the dawn of time. And what they're finding could shatter our most fundamental assumptions about reality itself. Think about that for a moment. The cosmic microwave background is like a cosmic fossil, a snapshot of the universe when it was just a newborn, barely 380,000 years old. But what if this ancient light carries secrets from even earlier, from a time before time as we know it? Theories like loop quantum gravity and string theory suggest our universe may have been born from the collapse of a previous one, like a phoenix rising from the ashes. If that's true, then the echoes of that long-lost cosmos could still be imprinted in the subtle ripples of the microwave background, waiting to be decoded. This isn't just about solving an abstract puzzle, it's about rewriting the story of existence. Detecting these echoes would mean peering beyond the Big Bang, into a realm where physics as we know it breaks down and new laws take over. It would challenge our very definition of beginnings and endings, suggesting that universes might rise and fall in an endless cosmic cycle. Over the next few minutes, we'll journey through mind-bending theories, cutting-edge experiments, and the thrilling possibility that we're on the verge of uncovering traces of a reality that predates our own. Buckle up, because this exploration will stretch your imagination to the very edges of what we think is possible. The Big Bang Theory stands as one of the most profound achievements in modern science, painting a vivid picture of our universe's explosive birth nearly 13.8 billion years ago. It tells us that everything we see, galaxies, stars, planets, all emerged from an unimaginably hot, dense point that expanded faster than the speed of light in a fraction of a second. But for all its explanatory power, the theory has a glaring blind spot. It describes what happened after the Big Bang, not what triggered it or what might have existed before. Think of it like pressing play on a movie. You see the story unfold, but you have no idea what happened during the filming or who wrote the script. The Big Bang Theory is the same. It gives us the universe's opening scene but leaves the backstory entirely blank. This isn't just a minor gap in our knowledge, it's a fundamental mystery lying at the very foundation of reality. Some scientists argue that the Big Bang wasn't a true beginning at all, but rather a dramatic transition from an earlier state of existence. Imagine walking into a room where a fire is burning. You see the flames, feel the heat, but what started it? Was it a spark from a match or the last ember from a previous fire? Similarly, the Big Bang could have been the rebirth of something older, a cosmic cycle where universes expand, collapse, and then expand again. This idea challenges the traditional view of a one-time creation event, suggesting instead that time itself might stretch far beyond what we once thought possible. If remnants of a pre-Big Bang universe do exist, they'd be incredibly subtle, like faint fingerprints left on the fabric of space-time. The key to finding them might lie in the cosmic microwave background, the oldest light in the universe. Just as archaeologists uncover hidden histories in ancient ruins, cosmologists search for anomalies in this radiation, tiny irregularities that don't fit the standard Big Bang narrative. These could be whispers from an earlier cosmic era waiting to be decoded. So while the Big Bang Theory remains our best framework for understanding the universe's evolution, it's clear that the story doesn't end there, or perhaps doesn't even begin there. The unanswered questions push scientists toward bolder ideas, daring to explore what might have come before the beginning we thought we knew. The cosmic microwave background is like the universe's baby picture, captured when it was just a cosmic infant. This faint glow fills every corner of space, a relic from a time when the universe was only 380,000 years old. Back then, the cosmos was a scorching plasma soup, too hot for atoms to form until it finally cooled enough for light to break free and travel across the vast expanse. Today, that ancient light has stretched into microwave wavelengths, creating a nearly uniform background hum that astronomers can detect with sensitive instruments. But here's where things get fascinating. The CMB isn't perfectly smooth. Tiny variations in temperature fluctuations as small as 1 part in 100,000 paint a detailed map of the early universe's structure. These minuscule wrinkles are the cosmic seeds that eventually grew into the galaxies and galaxy clusters we see today. They tell us how matter clumped together in those first moments, setting the stage for everything that followed. Yet some scientists suspect this glow might hold even deeper secrets. What if those subtle irregularities aren't just from the early universe, but carry imprints from something far older? Imagine throwing a stone into a pond. The ripples spread outward, but if you look closely, you might find faint echoes bouncing back from submerged objects. Similarly, anomalies in the CMB could be reflections from a time before the Big Bang, subtle disturbances left by events that occurred in a previous cosmic cycle. The discovery of the cosmic microwave background itself was almost accidental. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent hiss in their antenna, a noise they initially blamed on pigeon droppings. After eliminating every possible interference, they realized they'd stumbled upon the afterglow of creation itself. That moment revolutionized cosmology, turning the Big Bang from a speculative idea into concrete science. Now, decades later, we're at another threshold, wondering if this same glow might reveal an even more astonishing truth, that our universe has a backstory we're only beginning to uncover. Advanced telescopes like the Planck satellite have mapped the CMB with breathtaking precision, revealing patterns that don't quite fit our standard models. Some regions appear colder or hotter than they should be, while others show unexpected alignments. Could these be statistical flukes, or might they be the fingerprints of a pre-Big Bang universe? The answer lies in peeling back the layers of this cosmic onion, searching for signals buried beneath billions of years of cosmic evolution. Understanding the CMB is like decoding the universe's first language. Every fluctuation, every irregularity is a syllable in a grand cosmic story, and if we listen carefully enough, we might just hear whispers from a time before time began. What if the Big Bang wasn't the ultimate beginning but just one dramatic moment in an infinite cosmic symphony? The idea that our universe emerged from the ashes of a previous one isn't science fiction. It's a serious possibility explored by cutting-edge physics. Picture a cosmic pendulum swinging between expansion and collapse over unimaginable eons. In this view, the Big Bang becomes less like a singular creation event and more like the turning of a page in an endless cosmic storybook. Loop quantum gravity, a framework aiming to reconcile Einstein's general relativity with quantum mechanics, paints a particularly vivid picture. It suggests that before our universe existed, another one may have collapsed under its own gravity. But instead of vanishing into nothingness, it rebounded in a spectacular event called the Big Bounce. Think of it like squeezing a spring. At some point, the pressure becomes too great and it snaps back with tremendous energy. In this scenario, the dense, hot state we call the Big Bang was actually the moment when a previous universe's collapse reversed course, giving birth to our own. String theory offers another compelling angle. Some versions propose that our universe exists on a three-dimensional brane floating in a higher dimensional space. Collisions between these branes could trigger cosmic rebirths like sheets of paper smacking together in a cosmic wind, each collision creating a new universe with its own Big Bang. If this sounds mind-bending, that's because it is. We're talking about physics operating at energies 1 trillion times higher than anything we can recreate in particle accelerators. The most tantalizing part, these theories suggest that scars from these pre-Big Bang events might still be visible today. Just as tree rings record ancient droughts and volcanic eruptions, the cosmic microwave background could bear subtle patterns from our universe's cosmic ancestry. Some models predict concentric circles or spiral patterns in the CMB, ghostly imprints from collisions or quantum fluctuations in the previous cosmic cycle. Others suggest strange alignments in the microwave background's polarization that don't fit standard Big Bang predictions. Of course, not all physicists are convinced. Skeptics argue that without direct evidence, these ideas remain in the realm of mathematical speculation. But that's precisely why the search for these cosmic echoes is so thrilling. It's like being handed a damaged, ancient manuscript and trying to reconstruct the story that came before the first surviving page. Every anomaly in the CMB becomes a potential clue, a whisper from a time when the laws of physics as we know them may have been fundamentally different. What makes these theories so revolutionary isn't just their challenge to our cosmic origin story, it's how they transform our understanding of time itself. If the universe cycles endlessly through birth and rebirth, then the very idea of a beginning becomes fluid. Time might not be a straight line from past to future, but more like a vast cosmic spiral, with each turn containing entire universes with their own histories and futures. This perspective doesn't just change cosmology, it changes how we see our place in the grand scheme of existence. The hunt for these pre-Big Bang echoes isn't just about satisfying scientific curiosity. It's about uncovering whether our universe is a one-time marvel or part of something even grander, an infinite cosmic tapestry where every thread is a universe with its own story. As we peer deeper into the microwave background's subtle patterns, we might be reading not just our own history, but the last chapter of a story that began long before our cosmos existed. If we're searching for echoes from a universe that existed before the Big Bang, we need to know exactly what to look for in the cosmic microwave background. Picture the CMB as a vast, intricate tapestry, one where most threads follow a predictable pattern, but a few might weave in unexpected ways. Scientists scrutinize this tapestry for anomalies, tiny irregularities that don't quite fit the standard model of cosmology. These could be subtle temperature variations, patches of the sky that are slightly hotter or colder than they should be, or unusual polarization patterns, like faint swirls in the light's orientation that hint at something deeper. One of the most intriguing possibilities is the presence of concentric rings or spiral patterns in the CMB. Imagine throwing a pebble into a pond and watching the ripples spread outward. Now imagine those ripples freezing in place, preserved for billions of years. Some theories suggest that if our universe was born from the collapse of a previous one, the energy released during that transition could have left behind similar circular imprints in the microwave background. These wouldn't be obvious to the naked eye, they'd be buried in the data, requiring sophisticated statistical tools to uncover. Another telltale sign might come from the way the CMB's fluctuations align. Normally, these variations should be randomly distributed, like static on an old television. But if certain regions show strange correlations like temperature dips that line up in unexpected ways, it could suggest interference from an earlier cosmic epoch. Some researchers have even proposed that these anomalies might form geometric patterns like hexagons or spirals, which would be nearly impossible to explain without invoking a pre-Big Bang phase. Detecting these signals isn't just about having powerful telescopes, it's about rethinking how we analyze the data. The noise is overwhelming, with interference from galactic dust, distant galaxies, and even instrumentation errors all masking potential echoes. Scientists use advanced algorithms to filter out this noise, searching for statistical outliers that stand out from the cosmic background. It's like trying to hear a whisper in a crowded stadium, where every other sound threatens to drown out the one you're straining to catch. What makes this search so electrifying is that if these echoes are real, they wouldn't just confirm a pre-Big Bang universe, they'd offer a rare window into physics operating at energies far beyond anything we can recreate in labs. The patterns we're hunting could be the fingerprints of quantum gravity, the elusive theory that merges Einstein's relativity with the quantum world. Each anomaly is a potential clue, a breadcrumb leading us back to a time before time as we know it. And yet, the challenge is immense. The universe has had over 13 billion years to erase or distort these signals, like a message written in sand and left to weather countless storms. That's why researchers continue refining their methods, developing ever more sensitive instruments and sharper analytical techniques to tease out these cosmic whispers. The hunt isn't just about finding answers, it's about learning how to ask the right questions of the universe itself. Quantum fluctuations are like the universe's hidden heartbeat, tiny, unpredictable vibrations that exist even in what we call empty space. Imagine a vast ocean where waves constantly rise and fall, except here, it's particles and energy flickering in and out of existence in the blink of an eye. These fluctuations aren't just a quirky side effect of quantum mechanics, they might hold the key to understanding what happened before the Big Bang. In the extreme conditions of a pre-Big Bang universe, these quantum ripples could have been amplified to cosmic proportions, leaving behind faint but detectable scars in the fabric of space-time. One of the most striking ideas is that these fluctuations didn't just vanish when the universe began. They were stretched and frozen into the cosmic microwave background during the Big Bang's explosive expansion. Think of it like pressing your hand into wet cement. The imprint remains long after the event. If that's true, then the subtle temperature variations we see in the CMB today might not just be random noise, they could be quantum whispers from a time before our universe existed. Some theories even suggest that these fluctuations could have created microscopic black holes or exotic particles in the pre-Big Bang era, whose remnants might still linger in the CMB's patterns like cosmic fossils. The real challenge is separating these potential signals from the background noise. Quantum fluctuations are incredibly subtle, and the universe has had billions of years to scramble any original patterns. It's like trying to reconstruct a symphony from a single note that's been playing on loop for eternity. Yet, if scientists can identify specific signatures, like unusual correlations in the CMB's polarization or telltale asymmetries in its temperature map, it could point directly to quantum gravity effects operating at energies far beyond anything we've ever observed. What makes this search so exhilarating is that it bridges two seemingly incompatible worlds: the quantum realm, where particles behave in bizarre, probabilistic ways, and the cosmic scale, where gravity shapes the fate of entire galaxies. If we can find evidence of pre-Big Bang quantum fluctuations in the CMB, it wouldn't just confirm the existence of an earlier universe, it could finally unlock the secrets of quantum gravity itself, the holy grail of modern physics. This isn't just theoretical speculation. Cutting-edge simulations are now modeling how quantum fluctuations might propagate through a pre-Big Bang phase and imprint on the CMB. By comparing these simulations with real data, researchers hope to spot anomalies that defy conventional explanations. The stakes couldn't be higher. If successful, we wouldn't just be rewriting the history of our universe, we'd be peering into the very laws that govern reality at its most fundamental level. Yet for all its promise, this line of inquiry is fraught with challenges. Quantum fluctuations are inherently random, and their effects on the CMB could easily be drowned out by later cosmic events. It's like trying to hear a single instrument in an orchestra playing at full volume. That's why scientists are developing ever more sensitive detectors and refining their statistical tools, hoping to tease out these elusive signals from the cosmic background. The deeper we dig into these questions, the more we realize how little we truly know. Quantum fluctuations remind us that even the vacuum of space is alive with possibility, a seething cauldron of potential that might have shaped the universe long before the Big Bang. If we can decode their echoes, we might finally answer one of the most profound questions of all. What came before the beginning we thought we knew? String theory takes us into a realm where the familiar laws of physics twist into something extraordinary. A universe not of particles, but of vibrating strings so small that if an atom were the size of our solar system, a string would be no larger than a tree. This elegant framework doesn't just aim to unify quantum mechanics and gravity, it rewrites the cosmic origin story entirely, one of its most startling proposals. That our universe might be a three-dimensional island or brain, floating in a higher dimensional space, like a sheet of paper drifting in a vast, unseen wind. And if another brain collided with ours in this hidden dimension, the titanic release of energy could have sparked the Big Bang itself. Picture two enormous sheets fluttering toward each other in slow motion. When they meet, the impact sends ripples surging across their surfaces, except here, those ripples become galaxies, stars, and the very fabric of space-time. This ekpyrotic scenario, derived from the Greek word for conflagration, suggests that what we call the Big Bang was less an explosion and more like the aftershock of a cosmic car crash. The energy from that collision would have imprinted itself on the newborn universe, potentially leaving faint but distinctive patterns in the cosmic microwave background. What would these signatures look like? Some models predict that brain collisions could create gravitational waves, ripples in space-time with unique frequencies, like cosmic tuning forks humming a note from the dawn of time. Others suggest that the CMB might show unusual swirls in its polarization, like fingerprints left by the twisting forces of colliding dimensions. These wouldn't be random. They'd follow mathematical patterns tied to string theory's intricate geometry, offering a direct link between abstract equations and observable reality. Yet string theory's vision of a pre-Big Bang universe isn't without controversy. Critics argue that the math is so complex it borders on untestable, and the higher dimensions it requires remain frustratingly out of reach. But supporters counter that the CMB anomalies we've already spotted, like the infamous cold spot or unexpected alignments in temperature fluctuations, could be the first clues. It's like finding hieroglyphics in a cave and realizing they might be fragments of a lost language describing a world before our own. The stakes couldn't be higher. If string theory's pre-Big Bang scenario is correct, it wouldn't just explain our universe's birth, it would reveal an entire multiverse of brains, each with its own physics, clashing and birthing new cosmic epochs in an endless cycle. The cosmic microwave background becomes more than a relic. It's a palimpsest with layers of history waiting to be decoded. And as telescopes grow more sensitive, we might finally glimpse the echoes of that collision, the moment our universe was born from the wreckage of something older. This isn't just about rewriting textbooks. String theory's radical propositions force us to confront the limits of human intuition. We're trying to understand events where space and time crumble, where dimensions fold and unfold like origami, and where the very idea of before and after loses meaning. The search for these echoes isn't just scientific, it's philosophical, pushing us to redefine what it means to exist in a cosmos far stranger than we ever imagined. Loop quantum gravity offers a radically different vision of cosmic origins, one where the Big Bang wasn't a beginning but a turning point in an endless cosmic dance. Unlike traditional theories that hit a mathematical wall at the singularity, this framework suggests space-time isn't infinitely divisible. Instead, it's woven from tiny, indivisible loops, a fabric so fine that even at the universe's most extreme densities, it can't collapse to a point. Imagine stretching a rubber band until it snaps back with a twang. In loop quantum gravity's big bounce, the universe behaves similarly. A previous cosmos contracts to a critical density, then rebounds in the explosive event we call the Big Bang. What makes this idea so compelling is how it sidesteps the singularity problem entirely. General relativity predicts that at the Big Bang, gravity becomes infinite and equations break down, a clear signal that we're missing part of the story. Loop quantum gravity's quantum-corrected equations show something astonishing. As the prior universe collapses, quantum effects create a repulsive force so powerful it halts the collapse and triggers the bounce. It's as if space-time has a built-in safety mechanism, preventing total destruction and recycling the universe instead. The echoes of this rebound might still be visible today. Just as a bell's shape determines its ring, the quantum geometry of the bounce could have left distinct vibrational patterns in the cosmic microwave background. Some models predict a telltale suppression of large-scale fluctuations in the CMB, like a cosmic fingerprint showing where the universe's expansion reset. Others suggest subtle asymmetries in the microwave sky, hints that the bounce didn't unfold perfectly uniformly. These signatures wouldn't just confirm a cyclical universe, they'd offer the first direct evidence of quantum gravity in action. Yet the theory isn't without its mysteries. If a prior universe existed, what governed its laws? Were they identical to ours, or does each cycle rewrite physics? Some loop quantum gravity models suggest constants like the speed of light or the strength of gravity might shift slightly between cycles, like a snow globe settling differently each time it's shaken. This raises a profound question. Could our universe's finely tuned conditions, perfect for life, be the result of countless previous bounces gradually sculpting the cosmos? The real test lies in the data. While current CMB observations don't yet show definitive bounce signatures, next-generation telescopes could change that. Imagine detecting a faint spiral pattern in the microwave background's polarization, a cosmic whirlpool left by the universe's rebound, or finding unexpected correlations between temperature fluctuations that point to quantum geometry effects frozen in time. These wouldn't just validate loop quantum gravity, they'd open a window into the universe's ancestry, showing us the shadow of whatever came before. What's at stake isn't just another scientific model, it's a complete reimagining of time's arrow. In this view, the Big Bang becomes less like a birth certificate and more like a passport stamp, marking one transition in an eternal journey. The universe doesn't explode from nothing, it transforms, carrying forward quantum memories of its past. As we peer deeper into the CMB's subtle patterns, we might be reading not just our own history, but the last chapter of a story that began long before our cosmos existed. The cosmic microwave background is supposed to be the universe's most democratic feature, a near-uniform glow where temperature variations appear random, like static on an old television. But when scientists mapped it in detail, they stumbled upon something unsettling, patterns that refuse to follow the rules. The most infamous is the so-called axis of evil, a bizarre alignment of hot and cold spots that stretch across the sky like a cosmic equator. According to standard cosmology, these fluctuations should be scattered randomly like dice thrown across a table. Instead, they seem to whisper of hidden order, as if the universe rolled snake eyes a few too many times. What makes this anomaly so provocative is how stubbornly it resists explanation. Some researchers argue it's just a statistical fluke, like flipping a coin 20 times and getting heads each time by sheer chance. But the odds of that happening are astronomically low, raising eyebrows about whether we're seeing the fingerprints of something deeper. Could these alignments be scars from a pre-Big Bang universe where the laws of physics operated differently? Imagine shaking a snow globe and watching the flakes settle into a perfect spiral. It shouldn't happen unless something guided their fall. Similarly, the axis of evil might hint at forces or structures that predate our cosmic dawn. Then there's the cold spot, a region of the CMB chillingly colder than models predict. At first glance, it could be a cosmic void, a vast emptiness where matter is unusually sparse. But its size and temperature profile don't quite fit. Some theorists propose a wilder idea, that it's evidence of a collision with another universe in the multiverse. Picture two soap bubbles gently bumping in a bath. The energy from that contact might have left a bruise on our cosmos, frozen into the microwave background. Skeptics counter that such interpretations leap beyond the evidence, but the very existence of these anomalies keeps the debate alive. The challenge lies in distinguishing signal from noise. The CMB is a palimpsest layered with interference from galaxies, dust, and even our own Milky Way. Teasing out genuine anomalies requires painstaking statistical analysis, like trying to hear a faint melody in a room full of static. Future missions like LiteBIRD or CMB S4 aim to map the microwave background with unprecedented precision, potentially revealing whether these oddities are cosmic glitches or something far more profound. What's at stake isn't just a technical detail, it's the foundation of our cosmic narrative. If these anomalies are real, they could force us to rewrite the story of the universe's birth, introducing plot twists from epochs before time began. But if they're mere illusions, their persistence reminds us how easily patterns can deceive, even in the cold, hard data of the cosmos. The answer, as always, lies in looking deeper, peeling back the layers of the universe's oldest light to see what truths or tantalizing mysteries still linger. When the Planck satellite launched in 2009, it carried humanity's most ambitious effort yet to decode the cosmic microwave background. This European Space Agency mission spent over 4 years scanning the sky with sensitivity so precise it could detect temperature variations as small as a millionth of a degree. The result, the sharpest image ever of the universe's infant years, a map so detailed it revealed wrinkles in space-time older than the first stars. Most of Planck's findings cemented what we already knew. The standard model of cosmology, with its dark matter and dark energy, fits the CMB's patterns remarkably well. But nestled in the data were stubborn outliers, anomalies that refused to fit the textbook narrative. One of the most puzzling is the hemispheric asymmetry, where one half of the sky shows slightly stronger temperature fluctuations than the other. It's as if the early universe couldn't decide on a uniform recipe, leaving one side of the cosmic loaf slightly denser than the other. Standard inflation theory struggles to explain this lopsidedness, leading some scientists to wonder if it's a relic from an earlier cosmic phase. Then there's the cold spot, an unusually frigid patch spanning hundreds of millions of light years. While some attribute it to a vast cosmic void, its extreme chill pushes the limits of that explanation. Alternative theories suggest it could be evidence of a collision between our universe and another bubble in the multiverse, or even a topological defect in space-time left over from a pre-Big Bang phase. Planck's data didn't solve the mystery. It deepened it, leaving researchers to wrestle with whether these features are statistical flukes or cosmic breadcrumbs pointing beyond the Big Bang. What makes Planck's legacy so enduring isn't just the anomalies. It's how the mission transformed our ability to test wild theoretical ideas against hard data. Before Planck, speculations about pre-Big Bang physics often lived in mathematical abstraction. Now, theorists can calibrate their models against exquisitely precise measurements, asking whether hypothetical quantum gravity effects or cyclic universe scenarios could produce the subtle deviations Planck observed. It's like upgrading from a blurry telescope to high definition suddenly. Details once dismissed as noise demand serious consideration. Yet for all its power, Planck also taught humility. Many hoped its data would decisively confirm or rule out exotic pre-Big Bang models, but the reality proved messier. The anomalies exist at the edge of statistical significance, teasing but not definitive. This ambiguity has fueled a new generation of experiments, from ground-based telescopes peering at specific CMB frequencies to proposed space missions aiming to map the microwave background's polarization with even finer precision. Planck didn't hand us answers, it handed us better questions, the kind that keeps scientists awake at night, chasing whispers from the dawn of time. The satellite's final act was poetic. After exhausting its coolant in 2313, it slipped into a silent orbit around the Sun, its instruments forever stilled. But its data remains alive, mined by researchers who continue to sift through its maps for clues we might have missed. In the hunt for pre-Big Bang echoes, Planck isn't just a tool, it's a torch passed forward, illuminating a path toward discoveries that could redefine our place in the cosmic story. The next generation of cosmic explorers won't be astronauts in spacesuits, they'll be cutting-edge telescopes orbiting Earth, armed with technology so precise it could spot a snowflake on the Moon. Leading this charge is LiteBIRD, a Japanese-led satellite mission set to launch in the late 2020s, designed to scan the cosmic microwave background with sensitivity 50 times greater than Planck's. But LiteBIRD isn't alone. A global fleet of next-generation observatories, from the ground-based CMB S4 in Chile's Atacama Desert to the proposed space mission PICO, are joining the hunt, each equipped with revolutionary detectors capable of measuring the CMB's faintest whispers. What makes these missions so groundbreaking isn't just their technical prowess, it's their focus on polarization, the subtle twisting of light waves that could hold the key to unlocking the universe's deepest secrets. Picture sunlight reflecting off a lake. The shimmering patterns reveal the water's surface motions. Similarly, the CMB's polarization encodes information about the universe's earliest moments, including potential gravitational waves from the Big Bang itself. But here's the tantalizing twist. Some models suggest these waves might carry imprints from even earlier, a primordial fingerprint left by quantum fluctuations in a pre-Big Bang phase. LiteBIRD ultra-sensitive polarimeters could detect these patterns, distinguishing between standard inflation and more exotic scenarios like a cosmic bounce or brain collision. The stakes are astronomical. If these missions uncover polarization signatures that defy conventional inflation, say, spiral patterns or unexpected alignments, it wouldn't just tweak our cosmic timeline, it could shatter it. Imagine finding a fossil that contradicts everything we know about evolution, or a hieroglyph that rewrites ancient history. That's the scale of potential discovery here. Even null results would be profound, ruling out entire classes of pre-Big Bang models and forcing theorists back to the drawing board. But the challenges are just as immense. The CMB's signal is buried under foreground noise from our own galaxy's dust and synchrotron radiation, like trying to hear a whisper in a hurricane. To overcome this, missions like CMB S4 will deploy 500,000 detectors across 2 continents, creating a noise-canceling headset for the cosmos. Others, like PICO, plan to orbit at Lagrange points where Earth's interference is minimal, offering a crystal-clear view of the primordial sky. The real excitement lies in the unknown. Previous missions like Planck and WMAP mapped the CMB's temperature variations, the what of the early universe. These new explorers aim to capture the how and why, probing the physics that drove the universe's birth. Could anomalous polarization patterns reveal quantum gravity effects at work in a pre-Big Bang era? Might concentric rings in the data point to a cyclical universe's rebound? The answers could redefine not just cosmology, but our very understanding of time and existence. As these missions prepare to launch, one thing is certain: the cosmic microwave background is no longer just a relic, it's a living archive, its pages still being deciphered. The next decade of CMB research isn't just about filling gaps in our knowledge. It's about discovering whether those gaps lead to entirely new chapters in the story of the cosmos. And with every new instrument pointed skyward, we're not just observing the universe's past, we're peering into the shadows of what might have come before. Detecting signals from a pre-Big Bang universe is like trying to hear a single violin playing in a hurricane. The cosmic microwave background is already faint, a whisper of radiation from the dawn of time, but buried within it, any echoes from an earlier cosmic epoch would be exponentially subtler, drowned out by the universe's chaotic symphony. Imagine standing in a crowded stadium, straining to catch one quiet conversation amid the roar of thousands. Now, scale that challenge to cosmic proportions, where the noise includes everything from galactic dust to the afterglow of stars, all layered over 13.8 billion years of cosmic evolution. To even attempt this, scientists have become masters of cosmic signal processing. They don't just look at the CMB, they dissect it pixel by pixel, using algorithms that can isolate patterns as delicate as a fingerprint on a frosted window. One approach involves searching for statistical anomalies in the temperature fluctuations, hunting for deviations that defy the randomness predicted by standard cosmology. Think of it like analyzing a piece of music for hidden harmonies. If one note keeps reappearing where it shouldn't, it might hint at a composer we didn't know existed. Another hurdle is distinguishing true cosmological signals from local interference. Our own Milky Way's emissions, distortions from gravitational lensing, and even instrumental noise from telescopes can mimic or obscure the very patterns researchers seek. It's like trying to study the surface of a pond while wind, boats, and passing fish constantly disrupt the water. To filter this out, teams use multi-frequency observations, comparing data across different wavelengths to separate cosmic whispers from terrestrial chatter. The Planck satellite, for instance, mapped the sky in 9 frequency bands, creating a cosmic noise cancellation system of unprecedented precision. But perhaps the greatest challenge lies in the sheer audacity of what's being proposed. We're not just looking for faint signals, we're looking for signals that might operate under entirely different physics. If a pre-Big Bang universe existed, its quantum gravity effects or cyclical dynamics could have left signatures that don't match our current equations. Researchers must walk a tightrope, balancing open-mindedness with skepticism, ensuring they don't mistake wishful thinking for discovery. Every anomaly must survive a gauntlet of statistical tests, peer review, and independent verification before it's taken seriously. Yet the tools are improving faster than ever. Machine learning now sifts through CMB data at scales impossible for human analysts, flagging irregularities that might otherwise go unnoticed. Future missions will deploy superconducting detectors cooled to near absolute zero, capturing photons with quantum-level precision. and collaborations like the Simons Observatory are pooling global resources to scan the microwave sky with resolutions that would have seemed like science fiction a generation ago. The quest isn't just technical, it's philosophical. If we succeed, we'll have touched a reality beyond our cosmic horizon, proving that time and space have depths we've only begun to fathom. But even failure teaches us something profound, that the universe guards its oldest secrets fiercely, and unraveling them demands not just better tools but better questions. While echoes from a pre-Big Bang universe would be revolutionary, scientists must first rule out more mundane explanations for the cosmic microwave background's oddities. Imagine you're a detective investigating a crime scene where every piece of evidence could either crack the case wide open or turn out to be a red herring. The CMB anomalies are no different. Each one could be a cosmic smoking gun or just a trick of the light. Take instrumental errors, for example. Mapping the microwave sky isn't like snapping a photo with your phone. Telescopes like Planck and WMAP had to scan the heavens for years, stitching together millions of data points while battling cosmic rays, temperature fluctuations, and even the faint glow of dust in our own solar system. A tiny miscalibration in a detector or an unaccounted-for thermal wobble could create artificial cold spots or phantom alignments in the data. It's like trying to measure the thickness of a hair with a ruler that might flex slightly. With every use, you'd get numbers, but are they real or just artifacts of your tools? Then there's the challenge of foreground interference. Our Milky Way isn't just a pretty spiral of stars, it's a noisy emitter of microwaves, with swirling clouds of dust and charged particles that can mimic or mask the CMB's subtle patterns. Even distant galaxies and galaxy clusters leave their fingerprints, bending and scattering the primordial light through gravitational lensing. Researchers have to painstakingly subtract these foregrounds like archaeologists brushing dirt off a fossil, knowing that any mistake in the cleanup could create false anomalies. Some of the CMB's most puzzling features, like the cold spot, might simply be shadows cast by vast cosmic voids we haven't fully mapped yet. But perhaps the most intriguing possibilities lie in undiscovered astrophysical processes. The early universe was a laboratory of extreme physics, where conditions existed that we can't replicate in any particle collider. What if quantum fields we don't yet understand left unusual imprints in the CMB? Or if phase transitions in the primordial plasma, like steam condensing into water droplets, created shock waves that froze into the microwave background? These wouldn't require a pre-Big Bang universe to explain, just new physics operating within the standard cosmic timeline. The scientific process here is ruthlessly methodical. Before declaring they've found evidence of a cosmos before ours, researchers must exhaust every conventional explanation, running thousands of simulations to see if random chance or known phenomena could produce the same anomalies. It's a cosmic version of Occam's razor. The simplest solution is often the right one, at least until proven otherwise. Yet this skepticism isn't a lack of imagination. It's what makes potential discoveries so thrilling. If an anomaly survives every test, if it stares back at scientists from the data after all other explanations have fallen away, that's when the real excitement begins. Because then, just maybe, we're not looking at noise or equipment glitches, but the faint, fading signature of a universe that existed before our own. If we could prove that our universe was born from the remnants of an earlier cosmos, it wouldn't just rewrite cosmology textbooks, it would unravel some of humanity's deepest assumptions about reality. For centuries, we've framed existence as a linear story with a clear beginning, middle, and end. But a pre-Big Bang universe shatters that narrative, replacing it with something far more mysterious, an endless cycle of cosmic death and rebirth, where every ending seeds a new beginning. This isn't just a scientific shift, It's a philosophical earthquake, forcing us to reconsider what time, causality, and even existence truly mean. Take the concept of time itself. In our everyday experience, time flows forward like an arrow, never looping back. But if universes can bounce from collapse to rebirth, time might be more like a spiral, a vast, cyclical process where the before and after of a Big Bang blur together. Think of it like the seasons. Winter doesn't truly end spring. It transforms into it. Similarly, a pre-Big Bang cosmos wouldn't be separate from ours. It would be part of an unbroken chain, stretching infinitely into the past and future. This challenges the very idea of a first cause, leaving us to wonder, if there's no definitive starting point, does the question, why does anything exist, even have an answer? Then there's the staggering implication for causality, the principle that every effect must have a cause. In a cyclical universe, cause and effect could twist into something far stranger. The laws of physics in a previous cosmos might have been different, meaning the rules we consider fundamental, like gravity or the speed of light, could be local, temporary quirks rather than eternal truths. Imagine a tree growing from a seed, only to produce a new seed when it dies. Now picture that each new tree grows with slightly different leaves or bark. In this cosmic metaphor, our universe's constants might just be one iteration's unique features, destined to shift again in the next cycle. This leads to even deeper questions about reality's nature. If traces of a pre-Big Bang universe exist in the CMB, they'd be evidence of a realm where the laws of physics as we know them didn't apply. It's like discovering a hidden room in your house filled with objects that defy logic, a chair that floats, a mirror that shows the past. Such a discovery would force us to confront whether our universe's structure is inevitable or just one possibility in an infinite tapestry of cosmic variations. Are we living in a typical universe, or is ours an oddball compared to others in the cycle? The line between science and metaphysics begins to blur here. Traditionally, science deals with observable, testable phenomena, while metaphysics wrestles with the nature of being. But if we're staring at echoes from a universe that predates time itself, that distinction collapses. We're no longer just studying the universe, we're grappling with its very essence. Ancient philosophies, from Hindu cosmology's endless cycles of creation and destruction to the Buddhist concept of dependent origination, suddenly find eerie parallels in cutting-edge physics. It's as if humanity's oldest myths were groping toward truths that only now, with telescopes and quantum equations, we're beginning to quantify. Yet for all its grandeur, this idea also carries a humbling corollary. Our universe might not be special. If cosmic rebirth is the norm, then the conditions that made life possible in our cosmos, the precise tuning of physical constants, the balance of forces, could be the result of countless trial and error cycles. Like a river carving a canyon over eons, each iteration might subtly refine the parameters until life becomes inevitable. Or perhaps we're just one roll of the dice in an infinite multiverse of possibilities. Either way, it redefines our place in the grand scheme, not as the singular protagonists of creation, but as fleeting observers in an epic far older than we'd ever imagined. The search for these echoes isn't just about satisfying curiosity. It's a quest to understand whether existence is a one-act play or an endless performance where the stage resets after each curtain call. And with every new anomaly in the cosmic microwave background, we're not just peering into the past, we're glimpsing the possibility that time, space, and reality itself are far stranger than we've dared to dream. One of the most persistent myths about the Big Bang is that it was some kind of giant explosion, a cosmic bomb detonating in empty space, flinging matter outward like shrapnel. But that mental picture gets almost everything wrong. The Big Bang wasn't an explosion in space. It was the explosive expansion of space itself, everywhere at once. Picture a raisin cake baking in the oven. As the dough rises, every raisin moves away from every other raisin, not because they're being pushed outward from a center, but because the entire cake is expanding uniformly. There's no edge, no center, just a stretching of the cosmic fabric carrying galaxies along for the ride. This misunderstanding leads to another common question. Where did the Big Bang happen? The answer is mind-bending. It happened everywhere. The universe wasn't a tiny speck floating in some void. It was the entire cosmos in an ultra-dense state. When we say the universe was smaller in the past, we don't mean it was crammed into a corner of some larger space. It was all there was, and it's been stretching ever since. Trying to point to a location for the Big Bang is like asking where the surface of a balloon began expanding. The question doesn't make sense because the balloon's surface is the entire landscape. The confusion deepens when we talk about a pre-Big Bang universe. If people struggle to grasp that the Big Bang wasn't an explosion, it's even harder to wrap their heads around the idea that something might have preceded it. Pop culture often portrays the Big Bang as an absolute beginning, a definitive time zero, but many physicists now see it as a transitional phase, like a cosmic reboot rather than a cold start. Imagine watching a movie where the screen suddenly cuts to black, then fades up on a new scene. The Big Bang might be that cut, not the opening credits. Another widespread misconception is that the universe needed empty space to expand into, but space isn't expanding into anything, it's simply becoming more space. Think of it like a grid drawn on a rubber sheet. As you stretch the sheet, the grid lines grow farther apart, but they're not moving into some external territory. The sheet itself is what's changing. This is why distant galaxies appear to recede from us faster than light can travel. It's not that they're moving through space at impossible speeds, but that the space between us is stretching, carrying them away like driftwood on a rising tide. These misconceptions matter because they shape how people engage with cosmology. When someone imagines the Big Bang as a fiery explosion in a void, they're working from a flawed foundation, one that makes concepts like cosmic inflation, dark energy, or a cyclical universe even harder to grasp. Clearing up these myths isn't just about accuracy, it's about opening doors to deeper wonder. The true story of space itself stretching, of a universe with no center or edge, of a possible existence before existence, is far stranger and more magnificent than any explosion in the dark. And that's the real magic of cosmology. It's not about memorizing facts. It's about retraining your intuition to see the universe as it truly is, a place where common sense often fails, where nothing can give birth to something, and where the answers we find only lead to questions grander still. Decoding the universe's oldest whispers isn't a job for one type of scientist. It's a grand collaboration where physicists, mathematicians, and data scientists each bring their own magnifying glass to examine the cosmic microwave background. Think of it like assembling a global team of detectives where one specializes in fingerprints, another in blood spatter patterns, and a third in digital forensics. The physicist might model how quantum fluctuations could imprint on the CMB, while the mathematician devises new tools to tease subtle patterns from the noise, and the data scientist builds algorithms to process petabytes of telescope observations without missing a single celestial clue. Take the hunt for concentric rings in the CMB, potential evidence of a pre-Big Bang universe's cyclic nature. Physicists first predicted these patterns using equations from loop quantum gravity. But spotting them requires mathematical techniques originally developed for analyzing ocean waves or stock market trends, repurposed to sift through the microwave sky's static. Meanwhile, computer scientists train neural networks to recognize these signatures, much like facial recognition software learns to pick out a friend in a crowded photo. Without this interdisciplinary cross-pollination, those faint cosmic fingerprints might stay forever hidden in the data. The challenges these teams face stretch beyond traditional boundaries. A physicist's model of quantum gravity might suggest looking for spiral patterns in the CMB's polarization, but actually finding them demands statistical methods so advanced they're often borrowed from fields like meteorology or epidemiology. It's as if researchers studying hurricanes suddenly found their math describing turbulence in the early universe. This unexpected synergy sparks breakthroughs like when mathematicians adapted Fourier transforms, tools normally used for sound engineering, to filter out galactic noise from CMB signals with surgical precision. What makes this collaboration so powerful isn't just shared techniques, it's fundamentally different ways of thinking. A physicist approaches anomalies asking, what laws of nature could explain this? While a data scientist might ask, is this pattern significant or just random noise? Together, they create a checks and balances system where bold theories meet rigorous statistical testing. When the Planck satellite spotted the infamous axis of evil alignment, it took teams of statisticians to calculate the odds of it occurring by chance, while theorists scrambled to propose mechanisms, from cosmic topology to pre-Big Bang relics, that might explain it. The human element here is just as crucial as the technical one. Breakthroughs often happen at whiteboards where a cosmologist's back-of-the-envelope calculation inspires a programmer to write new simulation code overnight. Or when a mathematician's pure abstraction unexpectedly cracks open a stubborn problem in gravitational wave analysis. These collaborations remind us that the universe doesn't compartmentalize itself into academic disciplines, it's a seamless whole, demanding we break down artificial barriers between fields to glimpse its true nature. As the next generation of CMB experiments comes online, this interdisciplinary dance will only intensify. Upcoming missions will generate data volumes rivaling global internet traffic, requiring distributed computing solutions borrowed from Silicon Valley. Analyzing the results will need machine learning architectures trained on both simulated universes and real-world noise patterns, and interpreting any anomalies will demand teams fluent in everything from string theory to Bayesian statistics. The search for pre-Big Bang echoes isn't just pushing the boundaries of cosmology, it's redefining how science itself works in the 21st century. The hunt for echoes from a pre-Big Bang universe isn't just happening in observatories, it's unfolding inside some of the world's most powerful supercomputers, where scientists recreate cosmic history in lines of code. These simulations are like time machines, letting researchers rewind the universe's clock to test wild theories that would otherwise be impossible to probe. Imagine building a virtual cosmos where the laws of physics can be tweaked at will, where you could dial up quantum gravity effects, simulate collisions between higher dimensional brains, or watch a collapsing universe rebound into a Big Bang. That's the staggering power of computational cosmology, where entire universes are born, evolve, and die inside silicon brains humming in climate-controlled rooms. The process starts with equations, mathematical frameworks like loop quantum gravity or string theory that describe how space-time might behave under extreme conditions. Translating these abstractions into testable predictions requires converting them into algorithms that can run on supercomputers with millions of processing cores. It's like teaching a machine to dream in the language of quantum fluctuations and cosmic expansion. One team might simulate how quantum ripples in a pre-Big Bang phase would stretch across a newborn universe, while another models how colliding brains could imprint spiral patterns on the CMB's polarization. The goal isn't just to create pretty visualizations, it's to generate synthetic skies that can be compared pixel by pixel with real telescope data. What makes these simulations so revolutionary is their predictive power. When the Planck satellite spotted the infamous axis of evil alignment, theorists didn't just scratch their heads, they fired up supercomputers to see if any pre-Big Bang models could produce similar anomalies. Some simulations suggested that a universe born from a cyclic bounce might leave faint concentric circles in the CMB's temperature map, like ripples frozen in a pond. Others explored whether quantum entanglement across a cosmic rebound could create unexpected correlations between distant sky regions. Each virtual universe becomes a laboratory, testing whether anomalies in our real cosmos are glitches or glimpses of something deeper. But these digital cosmos aren't perfect mirrors of reality. Simulating the entire universe at quantum-level detail would require more computing power than exists on Earth, so scientists have to make strategic simplifications, like focusing on a patch of space-time or approximating certain physical effects. It's akin to painting a landscape where you meticulously render the foreground but suggest the distant mountains with broad brushstrokes. Despite these compromises, the simulations are astonishingly precise. Modern codes can model the CMB's temperature fluctuations to within 1% of actual observations, creating a baseline against which exotic pre-Big Bang signatures can be measured. The real magic happens when simulation meets observation. Researchers use statistical tools to compare their virtual skies with real CMB maps, searching for mismatches that might hint at new physics. A simulated universe that consistently produces spiral polarization patterns matching the cold spot, for example, would be a smoking gun for certain string theory models. Conversely, if no simulation can reproduce the observed anomalies without breaking other known cosmological constraints, it might suggest those quirks are just cosmic static after all. This back and forth between digital and observational cosmology has already ruled out entire classes of pre-Big Bang theories while breathing life into others. Yet the simulations also reveal how much we don't know. Some models produce CMB anomalies eerily similar to real ones, but through completely different mechanisms, leaving scientists to wonder if they're seeing the same cosmic face with the wrong explanation. Other times, simulations uncover entirely new phenomena that telescopes should have spotted but haven't, forcing theorists to revisit their assumptions. It's a humbling reminder that even our most advanced digital universes are still crude approximations of a reality far more complex than we've yet imagined. As supercomputers grow more powerful and algorithms more sophisticated, these simulations will dive deeper into the quantum gravity frontier, perhaps even probing the moment of the Big Bang itself. Future codes might incorporate effects we can't yet quantify, like the interplay between dark energy and hypothetical pre-Big Bang fields. With each advance, we're not just building better models of the cosmos, we're learning how to ask it better questions, one simulated universe at a time. Gravitational waves, ripples in the fabric of space-time, might hold secrets even older than the cosmic microwave background. While the CMB captures a snapshot of the universe at 380,000 years old, gravitational waves could carry whispers from the very first moments after the Big Bang, or even from the cosmic upheavals that preceded it. Picture dropping a stone into a pond and watching the ripples spread. Now imagine those ripples have been traveling for billions of years, subtly warping space itself as they pass. That's the essence of primordial gravitational waves, and they could be our most direct link to the universe's most distant past. These waves aren't like the ones detected from colliding black holes or neutron stars. Those are the cosmic equivalent of splashy headlines, violent, localized events. Primordial gravitational waves, if they exist, would be more like a faint universal hum, a background vibration left over from the universe's birth throes. Some theories suggest they might even encode information from a pre-Big Bang phase, like echoes bouncing off the walls of time. If the Big Bang was indeed a transition from an earlier state, a bounce, a brane collision, or a quantum fluctuation, the gravitational waves generated in that cataclysm could still be washing over us today, imperceptibly stretching and squeezing space as they go. Detecting them would require instruments of almost unimaginable sensitivity. Current observatories like LIGO and Virgo are tuned to catch high-frequency waves from stellar collisions, but primordial waves would be far slower, with wavelengths stretching across light years. Proposed missions like the Laser Interferometer Space Antenna, or LISA, aim to fill this gap. Imagine a trio of satellites floating in space, millions of miles apart, laser beams connecting them like the strings of a cosmic violin. As gravitational waves pass through, they'd subtly alter the distances between the satellites, creating a detectable signal. It's like trying to measure the width of a hair changing by a fraction of an atom's size over the span of a continent. The real prize would be finding a specific fingerprint in these waves, a pattern that doesn't match standard Big Bang predictions. Some models of loop quantum gravity, for instance, predict that a pre-Big Bang collapse would generate gravitational waves with a unique spectral tilt, a kind of cosmic barcode distinguishing them from waves produced by inflation. String theory, meanwhile, suggests brane collisions could leave behind circular polarizations in the wave patterns, like the swirling marks a spoon leaves in honey. Spotting these anomalies would be like finding a fossilized footprint that doesn't match any known animal, proof of something ancient and entirely unexpected. But the challenges are staggering. The universe is awash with gravitational noise, from orbiting black holes to the rumble of distant galaxies, all threatening to drown out the primordial signal. Filtering out this cacophony requires not just better detectors, but smarter algorithms. Researchers are already developing machine learning tools that can sift through the data, much like noise-canceling headphones isolate a single voice in a crowded room. And even if the signal is found, interpreting it will demand a delicate dance between theory and observation, as physicists reverse engineer the wave's origins like detectives, reconstructing a crime scene from scattered clues. What makes this search so electrifying is its potential to cross-validate the CMB's secrets. If both the microwave background and gravitational waves point to the same pre-Big Bang scenario, say, a cyclic universe or a brane collision, it would be like solving a puzzle with two independent sets of pieces, each confirming the other's picture. Conversely, if they disagree, it might mean our theories need a radical rethink. Gravitational waves could even reveal epochs the CMB can't access, like the first fractions of a second after the Big Bang, when the universe was too dense for light to travel freely. This isn't just about adding another tool to Cosmology's toolkit. Gravitational waves could be the missing key to unlocking a deeper layer of cosmic history, one where time's arrow might not point in just one direction, and where the universe's birth was just another chapter in an endless story. As we stand on the brink of this new era of discovery, we're not just listening to the universe's vibrations, we're tuning into the echoes of a past that might not be as distant or as singular as we once believed. Every time we point a telescope toward the cosmos or launch a satellite to study the microwave background, we're making a choice, one that involves millions of dollars, countless hours of human labor, and resources that could theoretically be spent elsewhere. This tension lies at the heart of cosmological research. How do we justify investing in questions about the universe's origins when Earth faces urgent crises like climate change, poverty, and disease? It's not just an abstract dilemma. It's a real-world balancing act that scientists, policymakers, and society grapple with every funding cycle. Consider the price tag of missions like the James Webb Space Telescope or the upcoming LiteBIRD satellite projects costing billions over decades. For that same investment, we could build thousands of schools, fund malaria eradication programs, or develop renewable energy infrastructure. The ethical weight of these decisions isn't lost on astronomers. Many openly wrestle with whether peering into the cosmic dawn is a luxury we can afford when so many struggle with basic survival. Yet history shows that fundamental research often yields unexpected practical benefits. The technology behind digital cameras, Wi-Fi, and even life-saving MRI machines all trace their roots to pure physics research initially deemed impractical. The debate becomes even more nuanced when we examine who funds this research. Most major cosmology projects rely on government grants or international collaborations, meaning taxpayer money ultimately fuels these cosmic quests. This raises thorny questions about democratic oversight and priorities. Should the public have more say in whether we hunt for gravitational waves or map the CMB's polarization? Some argue that science shouldn't be subject to popular vote, as groundbreaking discoveries often emerge from pursuits that seemed esoteric at the time. Others counter that in an era of shrinking budgets and growing inequality, every dollar must be justified by tangible societal impact. There's also the issue of global equity. While wealthy nations invest in probing the Big Bang, many developing countries lack basic astronomical infrastructure. Initiatives like the African Millimeter Telescope aim to bridge this gap, but the disparity remains stark. Could the pursuit of universal knowledge become more ethical by democratizing access to the tools of discovery? Some observatories now allocate observation time to astronomers from underrepresented regions, while open data policies allow global access to cosmic microwave background datasets. These small steps acknowledge that the universe belongs to everyone, not just those with the resources to study it. Yet dismissing cosmology as a frivolous indulgence misses a profound truth. Understanding our cosmic origins shapes humanity's self-awareness in ways that ripple through culture, philosophy, and even global cooperation. The famous Earthrise photo from Apollo 8 didn't cure disease, but it sparked an environmental movement by revealing our planet's fragility against the cosmic void. Similarly, discovering we're part of an infinite cycle of universes could fundamentally alter how we value our brief moment in cosmic history. Perhaps the most ethical choice isn't between practical and pure science, but in recognizing that exploring the universe's deepest mysteries is part of what makes us human, a timeless drive that has, time and again, illuminated our path forward in unexpected ways. Translating the mind-bending complexities of pre-Big Bang cosmology into something relatable isn't just helpful, it's necessary for science to thrive. Think about the last time you heard someone describe black holes or quantum entanglement in a way that made your jaw drop. That's the magic of great science communication, taking concepts that could fill chalkboards with equations and turning them into stories that spark genuine awe. When it comes to ideas as abstract as echoes from a universe before our own, the challenge is even greater. How do you explain quantum gravity's imprint on the cosmic microwave background to someone who's never taken a physics class? The answer lies in finding the right metaphors, the right hooks, and above all, the right human connections. Take the cosmic microwave background itself. To a scientist, it's a treasure trove of data, temperature fluctuations, polarization patterns, spectral distortions. But to most people, it's that static on old tube TVs, the snowy haze between channels. That's where communicators step in, reframing the CMB as the universe's oldest baby picture. a snapshot from its infancy that we're only now learning to decode. Or consider the wild idea of a cyclic universe. Instead of drowning audiences in equations about brane collisions or quantum bounces, storytellers might compare it to a phoenix rising from ashes, an endless cycle where each universe's death seeds the next birth. These aren't simplifications, they're bridges connecting abstract math to the imaginative worlds we already inhabit. The stakes go beyond just making science palatable. Public engagement fuels the entire scientific ecosystem, from inspiring the next generation of cosmologists to securing funding for ambitious missions. When a teenager watches a YouTube video explaining how gravitational waves could carry whispers from before the Big Bang, that's not just entertainment, it's potential ignition for a lifelong passion. And when taxpayers understand why mapping the CMB's anomalies matters, they're more likely to support the telescopes and supercomputers that make those discoveries possible. This isn't about dumbing down, it's about opening doors, showing that the universe's grandest mysteries belong to everyone, not just those fluent in tensor calculus. Some of the most effective communicators borrow techniques from unexpected places. Podcast hosts might structure cosmology like a true crime mystery, with each anomaly in the microwave background as a clue in a billion-year-old cold case. Planetarium shows use immersive visuals to let audiences travel back to the Big Bang, feeling the heat and chaos of creation rather than just hearing about it. Even social media has become a frontier, with threads and reels breaking down pre-Big Bang theories into bite-sized, shareable moments, the common thread. Recognizing that curiosity is universal, even if the knowledge isn't, yet there's a tightrope to walk. Oversimplify, and you risk distorting the science, overwhelm with jargon, and you lose your audience entirely. The best communicators navigate this by grounding even the wildest concepts in everyday experiences. Dark energy becomes the anti-gravity, pushing your coffee cup away if you could zoom out to cosmic scales. Quantum fluctuations, they're like tiny bubbles constantly forming and popping in the fabric of space-time. These analogies aren't perfect, no metaphor survives first contact with a physicist's red pen, but they create footholds for understanding, places to start asking better questions. What's truly remarkable is how this dialogue flows both ways. Public curiosity often pushes scientists to clarify their own thinking, stripping away academic scaffolding to reveal the core ideas beneath. When a child asks why the Big Bang couldn't have had A before, it forces researchers to articulate the limits of current theories with refreshing honesty. In this sense, science communication isn't just outreach, it's a vital feedback loop, keeping cosmology tethered to the human experience, even as it ventures into realms where intuition fails. The ultimate goal isn't just to inform, but to instill something deeper, a sense of shared wonder at the fact that we, tiny and fleeting as we are, can even contemplate the universe's origin. Whether through documentaries, podcasts, or planetarium shows, the message remains the same. These aren't just puzzles for experts in lab coats. They're part of humanity's grand conversation, stretching back to the first time someone looked up at the stars and asked, "Where did all this come from?" By bringing pre-Big Bang cosmology down to Earth, communicators ensure that conversation continues, richer and more inclusive with every voice that joins in. Before the Big Bang theory reshaped our cosmic origin story, most scientists believed in the steady-state model, a universe with no beginning or end, eternally expanding while continuously creating new matter to maintain its density. Picture an infinite loaf of raisin bread rising in the oven, with new raisins popping into existence to keep the spacing uniform as the dough stretches. This elegant idea, championed by astronomers like Fred Hoyle in the mid-20th century, appealed precisely because it avoided the messy notion of a singular creation event. It painted the cosmos as timeless and unchanging in its overall appearance, a comforting vision that aligned with the philosophical preferences of the era. Then came the cosmic microwave background, when Penzias and Wilson accidentally discovered this faint afterglow in 1965. It struck a blow to steady-state cosmology. Here was direct evidence of a hotter, denser past, a relic from an epoch when the universe was fundamentally different. The CMB's near-perfect blackbody spectrum matched predictions made years earlier by Big Bang theorists like George Gamow, who envisioned the early universe as a seething plasma that cooled as space expanded. Suddenly, the steady-state model looked like a beautiful theory slain by an ugly fact, but resistance lingered. Hoyle himself famously coined the term Big Bang as a dismissive label during a radio interview, never imagining it would become the name of the paradigm shift that overturned his life's work. This historical pivot holds profound lessons for today's hunt for pre-Big Bang echoes. Major cosmological shifts rarely happen overnight. The Big Bang's acceptance took decades, battling skepticism from establishment figures who found the idea of a cosmic beginning uncomfortably close to religious creation narratives. Even after the CMB discovery, alternate explanations were proposed. Perhaps the radiation came from scattered starlight or interstellar dust. It wasn't until satellite observations in the 1990s mapped the CMB's minute fluctuations with exquisite precision that the Big Bang achieved near-universal consensus. The process was messy, contentious, and deeply human, a reminder that science advances not just through data, but through the collective willingness to abandon cherished assumptions. Now imagine history repeating itself. If anomalies in the CMB or gravitational wave background do point to a pre-Big Bang phase, we should expect similar resistance. Some will argue the patterns are statistical flukes, others will propose less radical explanations. After all, challenging the Big Bang singularity is no small feat. It's questioning the very definition of time's 0 point. Yet history shows that today's heresies often become tomorrow's textbooks. The steady-state model's fall teaches us that even the most elegant theories must yield when nature whispers otherwise. What's different this time is the sheer breadth of tools at our disposal. Mid-20th century astronomers had rudimentary radio telescopes. We now have space observatories, quantum detectors, and supercomputers that can simulate universes. The steady-state theory fell because it couldn't explain new observations. If the Big Bang model is incomplete, its successor will need to account not just for the CMB, but for dark energy, quantum gravity effects, and the universe's large-scale structure, a far taller order. Yet the parallels remain striking. Once again, we're peering into the unknown, wondering if the foundations of cosmology are about to tremble. The lesson isn't just that science evolves, it's that the biggest breakthroughs come from listening carefully when the universe contradicts our stories about it. Not every cosmologist is convinced that the cosmic microwave background holds echoes from a universe before our own. For many researchers, the anomalies we've spotted, those strange alignments, cold spots, and unexpected patterns, are nothing more than cosmic coincidences, statistical flukes in a vast and messy dataset. Imagine flipping a coin 1,000 times and getting 10 heads in a row at some point. It might feel significant, but given enough trials, even rare sequences are bound to appear. That's how some scientists view the CMB's quirks, not as whispers from a pre-Big Bang era, but as random noise we've mistakenly given meaning. The skepticism runs deeper than just statistical caution. Critics point out that many pre-Big Bang models rely on untested physics, ideas like quantum gravity or higher dimensional brains that remain tantalizingly out of experimental reach. It's one thing to write equations describing a universe before time. It's another to prove those equations correspond to reality. Without direct evidence, these theories risk drifting into the realm of mathematical storytelling, where elegant solutions don't always translate to observable phenomena. Some argue that invoking a pre-Big Bang universe is like using a sledgehammer to crack a nut, an overly complex solution when simpler explanations, like instrumental errors or unaccounted galactic dust, might suffice. Take the infamous axis of evil, for example. While some theorists see it as a potential fingerprint of a cyclical cosmos, others note that our own Milky Way's magnetic field could be subtly distorting the CMB's polarization, creating phantom patterns that look profound but are really just local interference. Similarly, the cold spot might not be a bruise from a colliding multiverse. It could simply be a vast, underdense region of space, a cosmic void that's rare but not impossible under standard cosmology. The burden of proof, skeptics argue, lies with those making extraordinary claims. Before we rewrite the universe's origin story, we'd better be sure we're not just seeing shadows on the cave wall. This skepticism isn't just obstructionism, it's the engine of scientific progress. Every revolutionary idea, from plate tectonics to the Big Bang itself, faced fierce resistance before the evidence became overwhelming. Critics force theorists to sharpen their arguments, refine their models, and hunt for clearer signals. When a team claimed in 2014 that they detected primordial gravitational waves, potentially a smoking gun for inflation, it sparked a frenzy of follow-up studies that ultimately revealed the signal was likely galactic dust. The process was messy, but it underscored the importance of rigor. Yet the debate isn't purely academic. Funding for cosmology is finite, and every dollar spent chasing pre-Big Bang echoes is a dollar not spent on other mysteries like dark matter or exoplanet research. Some scientists worry that the allure of before the Big Bang could divert resources from questions where breakthroughs are more imminent. It's the classic tension between high-risk, high-reward speculation and incremental, testable science. Both are vital, but balancing them is a tightrope walk. What's fascinating is how the controversy mirrors older cosmological battles. Just as steady-state theorists once dismissed the Big Bang as metaphysical, today's establishment often views pre-Big Bang models as untestable speculation. But history shows that today's fringe idea can become tomorrow's textbook fact if the evidence cooperates. The key is maintaining a dialogue where bold visions meet rigorous scrutiny, where imagination is tempered by skepticism, and where every anomaly, no matter how exciting, is put through the ringer before we call it a revolution. For now, the question remains open. The anomalies in the CMB might be cosmic fossils or they might be mirages. The only way to know is to keep looking with better telescopes, sharper algorithms, and an openness to being wrong. After all, science doesn't advance by clinging to dogma, but by daring to question it, even when the answers lead us to places stranger than we ever imagined. What if our universe isn't alone just one bubble in a frothing cosmic sea of infinite realities? The multiverse hypothesis takes the mind-bending idea of a pre-Big Bang universe and cranks it up to 11, suggesting that anomalies in the cosmic microwave background might not be echoes from our own past, but ripples from collisions with other universes entirely. Picture a bustling subway station where each train is a self-contained reality, humming along its own track, only occasionally brushing against another car with enough force to leave a dent. In this scenario, the CMB's strange cold spots or unusual alignments could be cosmic bruises from run-ins with neighboring universes, each operating under completely different physical laws. The math behind this idea stems from inflationary theory, which describes how our universe expanded exponentially in its first fraction of a second. Some versions suggest this inflation never truly stopped, it just paused here, while elsewhere in the multiverse, new bubbles of space-time keep inflating endlessly. These bubble universes might occasionally bump into one another, transferring energy in ways that imprint on their respective cosmic microwave backgrounds. It's as if you found a mysterious fingerprint on your window, only to realize it wasn't from anyone inside your house. It was left by a passerby from another world entirely. Critics argue this sounds more like science fiction than testable physics, but supporters point to concrete predictions. Certain multiverse models suggest these collisions would create distinctive disk-like patterns in the CMB's temperature map, asymmetric regions where the radiation is slightly hotter or colder than the surrounding area. The Planck satellite's data revealed a handful of these oddities, including the infamous cold spot, a stretch of sky chillingly underdense compared to standard models. While other explanations exist like a colossal cosmic void, the multiverse angle adds a tantalizing twist. What if it's not a void at all, but the shadow of another universe nudging ours long ago? The implications spiral outward from there. If multiverse collisions can leave marks, could we someday decode their physics from those scars? Imagine discovering that the CMB's anomalies aren't just statistical noise, but messages in a bottle from realities where gravity operates differently or time flows backward. The challenge, of course, is proving it. Unlike the cyclical universe or pre-Big Bang models, where echoes would follow predictable quantum patterns, multiverse imprints could be wildly inconsistent, each collision unique, like snowflakes in a blizzard of realities. This isn't just about adding another layer to cosmology. It redefines what universe even means. Instead of a singular, all-encompassing cosmos, we might be part of a sprawling multiverse where the constants of nature, the strength of gravity, the mass of electrons are set by random chance. In that light, our universe's life-friendly conditions aren't a miraculous coincidence, but an inevitable outcome of infinite possibilities. The CMB then becomes more than a relic. It's a cosmic border crossing, a place where the fabric of our reality thins enough to reveal the strangers on the other side. Yet for all its grandeur, the multiverse hypothesis faces a steep hurdle. If other universes are forever beyond our observational reach, how can we ever confirm they exist? Some theorists suggest looking for more subtle signatures, like gravitational waves with impossible frequencies or quantum entanglement that defies local causality. Others argue the very untestability of the idea makes it more philosophy than science. But history reminds us that yesterday's metaphysical speculation often becomes today's cutting-edge research. Black holes were once dismissed as mathematical curiosities before telescopes proved them real. As we scour the cosmic microwave background for clues, we're not just peering into our past. We might be glimpsing the edges of something far larger, a reality so vast our universe is just one note in an endless symphony. Whether the multiverse remains a provocative thought experiment or blossoms into measurable fact, it challenges us to rethink not just where we came from, but what we even means in a cosmos teeming with potential copies, variants, and entirely alien iterations of existence itself. The hunt for whispers from before the Big Bang demands tools so precise they border on the magical. Enter the next generation of cosmic microwave background detectors, where quantum mechanics meets engineering brilliance. At the heart of this revolution are superconducting sensors cooled to temperatures colder than deep space, capable of catching individual photons from the dawn of time with almost no distortion. Picture trying to hear a pin drop in a thunderstorm, then inventing earplugs that filter out every sound except that pin. That's the leap these technologies represent. Projects like the Simons Observatory in Chile's Atacama Desert are deploying tens of thousands of these sensors across sprawling arrays, transforming our ability to scan the microwave sky with microscopic resolution. What makes these detectors so extraordinary is their marriage of quantum physics and nanotechnology. Superconducting circuits, chilled to near absolute zero, lose all electrical resistance, allowing them to register the faintest microwave signals without adding thermal noise. It's like upgrading from a foggy bathroom mirror to an electron microscope when examining the CMB's subtle patterns. But the real innovation lies in multiplexing, packing hundreds of detectors onto a single chip, each tuned to different frequencies. This lets scientists peel away foreground interference from galaxies and dust like layers of an onion, revealing the pristine primordial signal beneath. The payoff could be monumental. With this sensitivity, researchers might finally spot the faint spiral patterns or concentric rings predicted by pre-Big Bang model signatures too subtle for previous telescopes to catch. Some detectors are even targeting the CMB's polarization with sub-arcminute precision, hunting for the faint swirled imprints of primordial gravitational waves. These could carry echoes of quantum fluctuations from a hypothetical bounce or collision that birthed our universe. Imagine decoding a message where the paper is the fabric of space-time, the ink is polarized light, and the writer is a universe that existed before our own. Ground-based observatories are just part of the story. Future space missions like PICO and LiteBIRD aim to bypass Earth's atmospheric interference entirely, orbiting with detectors so sensitive they could measure temperature variations 1,000,000 times fainter than what current satellites detect. LiteBIRD planned launch in the late 2020s will map the entire sky in multiple frequency bands, acting like a cosmic noise cancellation system to isolate the CMB's faintest whispers. The mission's superconducting detectors will operate at 0.1 Kelvin, just a whisper above absolute zero, where quantum effects dominate and every photon's energy can be measured with astonishing accuracy. Yet the challenge isn't just building better hardware, it's rethinking how we process the flood of data these instruments produce. A single observation run can generate petabytes of information, equivalent to streaming every movie ever made in HD, dozens of times over. Machine learning algorithms now sift through this deluge, trained to recognize the statistical fingerprints of pre-Big Bang physics hidden in the noise. Some teams are even borrowing techniques from cryptography and artificial intelligence, treating the CMB like a coded message where anomalies might be the universe's way of leaking secrets from beyond the Big Bang. The most exciting prospect, these advances aren't incremental, they are exponential. Detector sensitivity has improved 100-fold in the past decade alone, with another 100-fold leap expected by the 2030s. At this pace, we're not just polishing our cosmic eyeglasses, we're building telescopes that can see through the veil of time itself. Whether the anomalies we find confirm loop quantum gravity's bounce, string theory's brains, or something entirely unexpected, one thing is certain: the tools we're creating today will redefine how we interrogate the cosmos, turning what was once philosophical speculation into measurable science. And with every new sensor deployed, we're not just observers of the universe's story, we're becoming its archivists, piecing together fragments from a past we're only beginning to imagine. Unifying quantum mechanics and general relativity is like trying to blend oil and water. They operate by fundamentally different rules, yet both describe essential truths about our universe. Quantum mechanics governs the bizarre behavior of particles at microscopic scales, where objects can be in two places at once or instantly influence each other across vast distances. General relativity, on the other hand, paints space-time as a smooth, bending fabric shaped by mass and energy. The conflict arises when we push these theories to their limits, like at the moment of the Big Bang, or before it, where the universe was smaller than an atom yet contained all the energy we see today. Here, the equations of relativity predict infinite density, while quantum physics demands discrete, fluctuating values. It's a cosmic clash of titans, and resolving it may require rewriting the laws of physics as we know them. Pre-Big Bang cosmology amplifies this challenge by venturing into realms where even our most advanced theories falter. Imagine trying to reconstruct a shattered vase when some pieces are missing entirely, except the vase is the universe, and the missing fragments are the laws that governed its earliest moments. Some models, like loop quantum gravity, propose that space-time isn't infinitely divisible but woven from tiny, indivisible loops. This quantum structure could prevent the infinite densities of a singularity, replacing the Big Bang with a big bounce. String theory takes another approach, suggesting that particles aren't points but vibrating strings in higher dimensional space, with collisions between these dimensions sparking our universe's birth. Both ideas are compelling, but neither has produced definitive predictions testable with current technology. The heart of the problem lies in the energy scales involved. To probe the Planck epoch, the first fraction of a second after the Big Bang, we'd need particle accelerators the size of galaxies. Without direct experiments, theorists must rely on indirect clues, like anomalies in the cosmic microwave background or patterns in gravitational waves. It's like trying to deduce the rules of a chess game by only studying the final board position. Some researchers are turning to quantum simulations, using ultra-cold atoms or superconducting circuits to mimic conditions near the Big Bang in lab settings. These tabletop universes won't recreate cosmic history, but they might reveal how quantum effects warp space-time in ways general relativity can't describe. What makes this search so electrifying is the possibility of discovering entirely new physics. Just as quantum mechanics appended Newtonian certainty a century ago, a working theory of quantum gravity could overthrow our notions of causality, locality, or even time itself. Some models suggest that in a pre-Big Bang phase, time might not have flowed linearly but bubbled like a quantum foam, with cause and effect becoming fluid concepts. Others propose that the universe's fundamental constants, like the speed of light or the strength of gravity, aren't fixed but emerged dynamically from a more primal state. These aren't just tweaks to existing theories, they're revolutions waiting to happen, hidden in the equations we haven't yet dared to write. Yet the path forward is fraught with philosophical quandaries. If we can't observe the pre-Big Bang era directly, how do we judge which theories are science and which are speculation? Some argue that mathematical consistency alone should guide us, while others insist on testable predictions, no matter how indirect. The debate echoes the early days of quantum theory, when Einstein famously resisted the idea of a probabilistic universe, insisting that God does not play dice. Today, we face a similar crossroads, balancing the audacity to imagine realities beyond our current framework with the rigor to ground those dreams in observable truth. The stakes couldn't be higher. Successfully merging quantum mechanics and relativity wouldn't just solve the mystery of the Big Bang, it would unlock new technologies, reshape our understanding of black holes, and perhaps even reveal whether time itself had a beginning. Every anomaly in the cosmic microwave background, every unexpected gravitational wave signal, brings us closer to that breakthrough. Until then, theoretical cosmologists navigate this uncharted territory with equal parts imagination and skepticism, knowing that the next great leap in physics might lie hidden in the echoes of a universe we've only begun to imagine. Long before telescopes or quantum equations, humanity's oldest stories grappled with the same cosmic mysteries that preoccupy physicists today. The Hindu Rigveda, composed over 3,000 years ago, describes a universe that cyclically breathes, expanding and contracting in vast epochs called kalpas, each lasting billions of years. Norse mythology envisioned worlds emerging from the void of Ginnungagap, only to be consumed by fire and reborn anew in an endless loop. Even the ancient Mayans calculated time in grand cycles, with each era ending in transformation rather than annihilation. These aren't mere coincidences, they're evidence of a universal human instinct to see existence as something far grander and more interconnected than a single linear timeline. What's striking is how closely some myths mirror modern cosmological models. The Hindu concept of a day and night of Brahma, where universes manifest and dissolve like bubbles in an infinite ocean, uncannily resembles the Big Bounce theory in loop quantum gravity. Similarly, the Buddhist idea of dependent origination, where all phenomena arise from interconnected causes without a definitive starting point, parallels the scientific view that the Big Bang may not mark an absolute beginning but a transition from a prior state. These parallels suggest that ancient thinkers, lacking telescopes but rich in observation and intuition, arrived at profound insights about cosmic cyclicality through philosophical contemplation rather than equations. The stories differ in their metaphors but converge on a shared theme: destruction as a prelude to renewal. The Egyptian god Atum, for instance, was said to create the world from chaos before eventually returning to it, much like how a collapsing universe in theoretical physics might seed its own rebirth. Indigenous Australian Dreamtime stories describe ancestral spirits shaping the land in epochs that repeat across everyone, blurring past, present, and future into a timeless continuum. Even Western traditions, often framed around linear creation, contain echoes of cyclicity, like the biblical book of Ecclesiastes declaring, "There is nothing new under the sun," or the phoenix mythos of death and resurrection found in cultures from Greece to China. This cross-cultural resonance raises a provocative question. Were these myths merely poetic guesses, or did they tap into a deeper, almost archetypal understanding of cosmic rhythms? Some scholars argue that observing natural cycle seasons, lunar phases, life and death led early cultures to project similar patterns onto the cosmos. Others propose that these narratives encode lost knowledge or altered states of consciousness that revealed universal truths beyond ordinary perception. Whatever their origin, their endurance speaks to humanity's relentless drive to find meaning in the vast unknown, using the language of their time to articulate what science now explores with satellites and particle detectors. The contrast between ancient myth and modern cosmology also reveals something profound about how we seek truth. Where myths used gods and symbols to explain the ineffable, science relies on data and equations, yet both grapple with the same fundamental awe. When a physicist describes quantum fluctuations imprinting on the cosmic microwave background, they're not so far removed from a shaman interpreting the night sky as the scars of ancestral battles. Both are attempts to decode a universe that resists simple explanation, to find patterns in the chaos that help us navigate our place within it. Perhaps the most humbling lesson lies in how these parallels expose the limits of human perspective. Just as ancient cultures couldn't have imagined the Planck satellite mapping the afterglow of creation, we too might lack the framework to fully comprehend what preceded the Big Bang. Our best theories, quantum bounces, colliding brains, multiverses, could someday seem as quaint as creation myths appear alongside modern astrophysics. Yet this continuity across millennia reminds us that the quest to understand cosmic origins isn't just a scientific endeavor, it's a deeply human one, woven into our stories, our art, and our collective imagination. In the end, these mythological echoes don't validate or invalidate contemporary physics. but they illuminate something equally important: our shared longing to connect with the universe's deepest mysteries, whether through the sacred or the empirical. As we peer into the cosmic microwave background for traces of a pre-Big Bang era, we're participating in the same timeless dialogue that once unfolded around campfires and temple altars, a dialogue about where we come from and what it means to exist at all. Imagine a classroom where students aren't just memorizing equations, but holding the fabric of space-time in their hands literally. That's the magic of modern educational outreach in cosmology, where abstract concepts about black holes, the Big Bang, and multiverses become tangible adventures. Programs like NAS, a universe of learning, transform cosmic data into interactive experiences, letting kids manipulate 3D models of galaxy clusters or listen to the eerie sounds of gravitational waves translated from telescope data. It's not about dumbing down the science, it's about unlocking the wonder that already exists in questions like, what happened before time began? A question any curious child might ask, and one that even the most advanced physicists are still trying to answer. The secret lies in meeting young minds where their curiosity lives. Take the Cosmic Detectives workshops run by observatories worldwide, where students analyze real telescope images to spot supernova or exoplanets. One middle schooler in Chile recently flagged a subtle dip in starlight that turned out to be a previously unknown planet candidate, proof that you don't need a PhD to contribute to real science. Other initiatives like the LEGO Team's Black Hole Hunter games use actual gravitational wave data to let players identify collisions between neutron stars. These aren't just educational tools, they're gateways showing kids that the universe's grandest mysteries aren't locked away in ivory towers but are puzzles anyone can help solve. But inspiration doesn't stop at screens and simulations. Mobile planetariums bring the cosmos to underserved communities, their domes blooming like jellyfish in school gymnasiums to immerse students in journeys from the Big Bang to the birth of galaxies. In rural India, the AstroSat Outreach program uses simple, locally built spectroscopes to teach kids how light reveals the chemistry of stars, proving you don't need multi-million-dollar gear to touch the stars. Meanwhile, programs like Girls Who Code Astrophysics are shattering stereotypes, pairing teenage girls with mentors who guide them through coding projects analyzing real CMB data. The message is clear: cosmology isn't just for a privileged few, it's a collective human adventure. The ripple effects of these efforts are already visible. When the James Webb Space Telescope launched, it wasn't just scientists celebrating. Classrooms worldwide tracked its deployment in real time, their excitement fueled by years of accessible astrophysics education. Some of those students will inevitably become the researchers who decipher JWST's most puzzling findings, or perhaps design the next generation of telescopes to probe pre-Big Bang echoes. The cycle feeds itself. Today's starry-eyed kid sketching spiral galaxies in a notebook could be tomorrow's pioneer, developing theories we can't yet imagine about what existed before our universe. Yet the challenge remains immense. In an era where STEM education often prioritizes practical careers like engineering or medicine, cosmology risks being seen as impractical, a luxury rather than a necessity. But history teaches us that fundamental curiosity drives unexpected breakthroughs. The same quantum mechanics that once seemed like abstract philosophy now underpins every smartphone and MRI machine. Who's to say the child today enthralled by cosmic inflation won't discover the physics that powers civilizations centuries from now? This isn't just about training future scientists. It's about nurturing a world where cosmic literacy is as foundational as reading or math, where understanding our place in the universe isn't niche knowledge, but part of being human. When a teenager in Nairobi or Quito gazes at a planetarium show and realizes those swirling galaxies are made of the same atoms as their own hands, it sparks something transcendent, the realization that we're not just observers of the cosmos, but active participants in its story. And that story, as we're only beginning to understand, might stretch far beyond the Big Bang into realms waiting to be explored by the next generation of cosmic dreamers. Science thrives when stargazers and equation wielders join forces, and nowhere is this collaboration more vital than in the hunt for echoes from a pre-Big Bang universe. Picture a cosmic detective story where the crime scene spans the entire sky, the evidence is encoded in faint microwave static, and the suspects are theories so abstract they defy everyday intuition. The observers, those who design telescopes and painstakingly map the cosmic microwave background, are the forensic specialists collecting every photon like fingerprints at a crime scene. The theorists, meanwhile, are the profilers constructing elaborate models of what might have left those marks. Without both teams working in lockstep, the clues remain indecipherable. Consider how this partnership played out with the infamous cold spot, that puzzling region of the CMB significantly cooler than standard models predict. When observers first flagged it, theorists rushed to propose explanations. Was it a statistical fluke, a colossal supervoid, or something more exotic, like a collision with another universe? Each hypothesis made testable predictions. If the cold spot was caused by a void, for instance, follow-up galaxy surveys should show a corresponding lack of matter. When those observations came up empty, it gave weight to wilder ideas, pushing theorists to refine their models. This back and forth isn't just academic, it's how science separates cosmic mirages from genuine breakthroughs. The synergy becomes even more critical when dealing with anomalies that might hint at pre-Big Bang physics. Observers might spot a strange pattern in the CMB's polarization, say, spiral swirls that don't match standard inflation predictions. Theorists then scramble to calculate whether such patterns could arise from quantum gravity effects during a big bounce, or from higher dimensional brane collisions. Their equations become a filter. If a model predicts swirls of precisely the size and shape observed, it earns credibility. If not, it's back to the drawing board. This iterative process is like tuning a radio. The observers twist the dial, hunting for signals in the static, while the theorists adjust the antenna's design based on what static they expect to find. Yet this collaboration isn't without friction. Observers often prioritize clean, unambiguous data, while theorists revel in elegant mathematics that may lack observational hooks. Bridging the gap requires a shared language, one where a statistician's 5 sigma detection translates meaningfully to a string theorist's Calabi-Yau manifold. Projects like the Simons Observatory now embed theorists in observational teams from the start, ensuring telescope designs can test today's most speculative ideas. It's a shift from reactive to proactive science, where instruments are built not just to confirm what we already know, but to probe what we've only dared to imagine. The stakes couldn't be higher. If pre-Big Bang echoes exist, they're buried under layers of cosmic noise and competing explanations. Isolating them demands both the theorist's vision to know where to look and the observer's rigor to prove what's really there. Like restorers cleaning an ancient fresco, they work millimeter by millimeter, one group removing centuries of grime, the other identifying the original brushstrokes beneath. Every anomaly that survives their combined scrutiny brings us closer to answering one of existence's ultimate questions. Are we the first universe or merely the latest in an infinite series? This partnership also guards against the seduction of false patterns. Human brains are wired to find significance in randomness, a tendency that's led to discoveries like the face on Mars or constellations in star fields. The observer theorist dynamic acts as a reality check, ensuring that tantalizing CMB quirks aren't just cosmic Rorschach tests, but genuine windows into physics beyond the Big Bang. When both sides agree that an anomaly withstands every test, that's when the real excitement begins, the moment a whisper from before time becomes a shout we can no longer ignore. Peering into the cosmic microwave background for whispers from before the Big Bang isn't just a scientific challenge, it's a societal choice. The telescopes capable of this detective work, like the upcoming LiteBIRD satellite or the groundbreaking Simon's Observatory, don't materialize out of thin air. They're the culmination of decades of funding, international collaboration, and political willpower, each project costing more than a blockbuster movie franchise. Yet, unlike Hollywood spectacles, the payoff here isn't measured in box office returns but in something far more profound: rewriting humanity's origin story. Consider the Hubble Space Telescope's journey. Conceived in the 1940s, it faced cancellation multiple times before finally launching in 1990, a 50-year saga of budget battles and bureaucratic hurdles. Today, Hubble's discoveries are household knowledge, from pinning down the universe's expansion rate to revealing galaxies at the edge of time. But none of that would have happened without sustained investment through shifting political winds and competing priorities. The same holds true for cosmology's next frontier. Detecting potential pre-Big Bang echoes requires instruments so sensitive they border on the miraculous superconducting detectors cooled to near absolute zero, space-based observatories free from Earth's atmospheric interference, and supercomputers to process data volumes rivaling global internet traffic. These aren't gadgets you can crowdfund. They demand national budgets and multinational treaties. The tension lies in justifying these costs when immediate needs: healthcare, education, infrastructure clamor for attention. Critics argue that probing the universe's origins is a luxury when millions lack basic necessities. But history reveals a counterintuitive truth: fundamental research often sparks unexpected revolutions in applied science. The same quantum mechanics that once seemed like abstract musing now powers every smartphone and MRI machine. The algorithms developed to analyze the cosmic microwave background have been repurposed to detect tumors in medical scans. Even the internet itself traces its roots to particle physicists at CERN needing to share data across continents. When we invest in cosmology, we're not just buying telescopes, we're seeding future technologies we can't yet imagine. Funding fundamental science is also a bet on long-term cultural capital. Think of how the Apollo program transformed a generation's view of what humanity could achieve, or how the discovery of exoplanets reshaped our cosmic perspective. A child today watching scientists debate pre-Big Bang physics might become tomorrow's pioneer in clean energy or artificial intelligence, inspired by the audacity to ask unanswerable questions. This cultural ripple effect defies traditional cost-benefit analysis. How do you quantify the value of a society that looks beyond immediate survival to ponder its place in an infinite cosmic tapestry? The policy landscape mirrors this delicate balance. Scientific megaprojects require stable funding across electoral cycles, a challenge when political priorities shift every few years. The James Webb Space Telescope's near cancellation in 2011 over budget overruns nearly cost us the stunning images now redefining astronomy. Conversely, the European Space Agency's Planck mission, which mapped the CMB with unprecedented precision, benefited from consistent multinational support despite its €1 billion price tag. The lesson is clear: Breakthroughs happen when societies commit to the long game, insulating science from the turbulence of short-term politics. Grassroots advocacy plays a surprisingly vital role here. When the U.S. National Science Foundation faced budget cuts in 2022 that threatened the CMB S4 project, a next-generation array of telescopes in Chile and Antarctica, thousands of astronomers and citizens lobbied Congress with a simple message: understanding the universe's origins isn't niche research, it's a fundamental human endeavor. The funding was restored, proving that public passion can sway policy. Similar movements have protected funding for gravitational wave observatories and dark matter experiments, demonstrating that cosmology's allure transcends academia. The stakes couldn't be higher. If anomalies in the CMB do hint at a pre-Big Bang universe, confirming them will require instruments even more advanced than those we've built. Without sustained investment, we risk leaving the greatest cosmic detective story half told, forever wondering what secrets might have lain in the static of the microwave sky. But if we rise to the challenge, the payoff could redefine reality itself, not just for scientists, but for every person who's ever gazed at the night sky and wondered, where did all this come from? That's the true value of fundamental research. It's not about answers we can predict, but questions we've yet to dream. The search for echoes from a pre-Big Bang universe isn't just about rewriting cosmic history, it's about discovering whether our universe is a solo act or part of an infinite cosmic symphony. Every anomaly in the cosmic microwave background, every unexplained pattern in the primordial light, could be a note from a score we're only beginning to decipher. Even if these signals turn out to be cosmic static, the very act of looking changes us. It stretches our understanding of time, space, and the nature of reality itself, proving that sometimes the journey matters as much as the destination. Consider how far we've come in just a century. 100 years ago, many scientists believed the Milky Way was the entire universe. The concept of a Big Bang was radical, even heretical. Today, we're debating whether space-time existed before that explosive moment, armed with telescopes that can detect whispers from the dawn of creation. This relentless curiosity, this refusal to accept "we don't know" as a final answer, is what propels science forward. Every dead end, every false lead, teaches us something new about how to ask better questions. What makes this quest so exhilarating is its unpredictability. The next breakthrough might come from a graduate student spotting an odd correlation in old satellite data, or from a supercomputer simulation revealing hidden patterns in quantum fluctuations. It could emerge from a lab experiment mimicking conditions near the Big Bang, or from a telescope so sensitive it detects gravitational waves from the universe's first trillionth of a second. The tools we're building today, like the LiteBIRD satellite's ultra-precise polarimeters or the gravitational wave observatories listening for spacetime's faintest tremors, are opening doors we didn't even know existed a generation ago. But the real magic lies in the questions we haven't thought to ask yet. Every major discovery in cosmology has blindsided us in some way: dark energy, inflation, the accelerating expansion of the universe. None were predicted before they were observed, reminding us that the cosmos is always stranger than our boldest theories. If echoes from a pre-Big Bang universe are out there, they'll likely defy our current frameworks, forcing us to invent new physics to make sense of them. That's the beauty of science. It's not about confirming what we already suspect, but about being humbled by what we've yet to imagine. And so the search continues, not because we're guaranteed answers, but because the universe keeps surprising those brave enough to listen. Whether we uncover proof of a cyclic cosmos, a multiverse collision, or something entirely unforeseen, one thing is certain: the cosmic microwave background is more than ancient light. It's a message in a bottle floating across billions of years, waiting for us to decode its deepest secrets. The next chapter of this story isn't written in the stars. It's being written by the scientists, engineers, and dreamers who dare to ask, what came before the beginning? And that, perhaps, is the most thrilling revelation.